All right, ladies and gentlemen, welcome back to another video with Mr. Kenton for HL Chemistry, and we're going to be continuing our lessons on topic 2, which is focusing in on atomic structure, and we're going to look at what I think is a pretty fascinating section, which looks at the different models of the atom that were developed over time. And I think this is one of the clearest pictures of how when scientists gain new information and they're operating from a specific model, that the model has to change in order to best match up with what's being experimentally observed and what matches up with reality. And so looking at the models of the atom, we're going to see lots of big changes that happen and how scientists were ever able to get to that point to make those changes as a whole. So I'm excited to actually present this to you because I don't think this is something we get to really spend a lot of time on in AP chemistry, but I think it's a fascinating topic. So let's just dive right in here. So you got different models of the atom. So the first model of the atom is really based off of John Dalton and his work with Dalton's atomic theory. Then you're going to have the Plum pudding model, where J.J. Thomson discovers the electron. Next, you've got Ernest Rutherford, who, through the gold foil experiment, discovers the proton that's within the atom. Then you've got Niels Bohr, who develops our solar system-like model, where the electrons orbit the nucleus at specific distances and the electrons exist in specific energy levels. And then we lead to our final model, which is what you guys learned about in AP chemistry and honors chemistry, the quantum mechanical model, which is our modern theory, where the electrons exist in cloud shapes or orbitals that are based on probabilities, the probability of finding an electron within a specific location. All right. Now we're going to take some time to walk through each of these models and how they contributed to our current understanding of the atom today. Now let's start with John Dalton and his atomic theory. So Dalton's atomic theory is based on 5 principles, or 5 assumptions, if you will. The first one is that all elements are composed of atoms. It's a pretty straightforward statement. All elements are composed of atoms. That makes sense. The second statement is that each element has atoms that are different from the atoms of any other element. That's just simply to say atoms are different because they have different numbers of protons. Like, that's how we would kind of frame that today, right? So we know that an atom of nickel is different from an atom of chlorine, right? Has to do with the number of protons that are in the nucleus, the number of electrons that they have, different things like that. So different properties, all those different things, based on the fact that they have different numbers of subatomic particles. The third thing, atoms cannot be subdivided, created, or destroyed. So again, this was Dalton's atomic theory. This is assumptions. These are things that he was laying as groundwork when he was talking about atoms collectively. Fourth, atoms of different elements combine in simple ratios to form chemical compounds, right? We see that happen all the time. We know that to form water, 2 atoms of oxygen or of hydrogen have to interact with 1 atom of oxygen in order to form water. Right? Again, that's pretty intuitive. That makes a lot of sense. Now, the fifth thing that Dalton's atomic theory presented is that one type of atom cannot be changed into another type of atom by a chemical reaction. And I think it's important here that we mention it from the perspective of a chemical reaction. Because if you recall, chemical reactions are essentially modeling and looking at transfers and changes in electrons between different elements or atoms, whereas within nuclear chemistry, that's when you've got changes that are taking place inside the nucleus itself. So one type of atom cannot be changed into another type of atom by any chemical reaction. That makes sense. Now, as we look at those 5 postulates or 5 assumptions that Dalton was operating under, we can certainly see that some of them definitely still have precedence and value today. However, we can also notice that some of those assumptions are simply just not true. Now, again, not all aspects of Dalton's theory prove to be correct, We learned that atoms can be subdivided. That's why you can have protons, neutrons, and electrons. And if you break it down even farther, that's why you can have quarks. And that's why you can have matter versus antimatter, right? So we can see that atoms can, in fact, be subdivided. They can be broken down into smaller parts. The next thing that we notice is that atoms can have different masses. So they can still be the same atom, but have a different mass, have a different isotope because of the number of neutrons that are found in the nucleus of that particular isotope. Now, the neat thing is that even though this was kind of our starting point for atomic theory, there are still parts of Dalton's theory that are relevant to us today. Now, the first thing, all matter is composed of atoms. That is a basic understanding that we operate under. That is still relevant today. That when we talk about anything that's matter, that has a mass and occupies space, it's composed of atoms. And the second thing is that atoms of one element differ in properties from those of every other element. Again, that's also a foundational principle that we still operate under even today. So even though not all of Dalton's atomic theory remained intact and in use, there are still parts of it that we use today to help us guide our understanding. All right, next we've got J.J. Thomson's model, which is commonly referred to as the Plum pudding model. Now, it's a weird name, but we'll kind of talk about the origins of that here shortly. Now, what Thomson discovered was that the electron had a negative charge. So what J.J. Thomson does is he adapts Dalton's model of the atom, and he says, all right, so we know we've got this atom, and he's going to display the negative electrons. He's going to say they're going to be suspended in a positive fluid. So if you're looking at the diagram that's kind of at the bottom, you've got the white portion of that diagram. That's going to be the positive gooey stuff. That's our positive fluid that our atom is made up of. And then the red dots are going to be the negative electrons that are held in place within that positive fluid. Now, kind of looks like a chocolate chip cookie, or you could think of it the plum pudding model. It's essentially, it was a type of British dish where you would have plums that are distributed throughout the pudding, if you will. That's where it kind of gets its name. And so, obviously, this kind of changed scientists' idea of how the atom was structured. So now we've got this positive gooey stuff. We've got a negative electron that's held in place within our atom. So here we no longer just have the atom itself. We've got these negative electrons that exist as well. All right, moving forward, then we move into Rutherfords model of the atom, which is going to be formulated based off of the gold foil experiment. Now, if you're not familiar, the gold foil experiment is what led to the discovery of the positively charged nucleus, and the nucleus being dense. Essentially, that's being where the majority of the mass of the atom is coming from. Right, so the nucleus contains the majority of the mass of the atom, and the electrons surround the central nucleus, and really what's surrounding the nucleus is mostly empty space. The electrons are in that mostly empty space. See, look at me, I'm getting ahead of myself. So most of the atom as we know it is actually mostly empty space. All right, and so in Rutherford's model, in the gold foil experiment, what happened is he was using alpha particles, which are essentially helium nuclei that have a positive charge. He was shooting them at gold foil, and for the majority of his experiment, what he found is that those alpha particles just simply passed through the gold foil. But there was a small number of particles that were being deflected. So rather than just passing straight through, they were being deflected at given angles, and some of them were even bouncing completely back to the alpha particle source. And so the reason why they were being deflected was because there was something positive inside the atom itself. And so based on those observations, that's how we determined that the nucleus had to have a positive charge. And so you can see how it's been adapted now. Instead of it being this positive fluid that's holding the electrons in place, you now have the positive charge being fixed in one location with the negative electrons around it. And again, where the white used to be, now you've got mostly empty space that's between the electrons and the nucleus. Now, as we start to think through the Rutherford model of the atom, that presents us with a problem. Because we think about Coulombic attraction, we know that when particles have opposite charges, Coulombic attraction says these particles are going to exert a force on each other that's going to attract them to each other. They're going to want them to get closer together. Right? We know they attract each other. So in this model, the problem that gets presented is, why don't the electrons just simply move into the nucleus? What is preventing these electrons from being on the outside? And so, though Rutherford was able to come up with this model, he wasn't really able to come up with a solution. So that's what's going to lead us into the Bohr model of the atom, because Bohr proposes a possible solution. He says, okay, instead of the electrons just hanging out around the nucleus, right? So instead of them just kind of being weirdly distributed there, which would ultimately lead them to crash into it because of the Coulombic forces of attraction, perhaps the electrons have specific energies. And maybe these specific energies, maybe the electrons are going to orbit the nucleus, kind of like the planets orbit the sun. So you think about it. In the solar system, the planets are not drawing closer to the sun. There's a force of gravity, certainly, that's keeping them on specific paths, but they're not moving closer or farther away from the sun, at least ideally, right? And so maybe the electrons are behaving in that particular way and are following this orbit that's preventing them from getting closer to the nucleus itself. And so then you get kind of your planetary model, which you probably saw in like Jimmy Neutron or something like that, right? Now, with the Bohrs model of the atom, a lot of very useful information can be gleaned from it that we use even today. So let's take a look at those things, right? So there's your kind of your Bohr model of the atom, where you've got a certain number of electrons in certain places in different orbits and different energies. So Bohr came up with the idea that the size of an electron's orbit was related to how much energy the electron had. Right? So that's just to say, if it's farther away from the nucleus, it has higher energy. Right? If it's closer to the nucleus, it's going to be lower in energy. So the energy level of an electron would determine how far away from the nucleus the electron would be. Electrons that are close to the nucleus are going to have relatively low energy. Electrons that are farther away from the nucleus are going to have relatively high energies. Now, in coming up with this idea that the energy of the electron was related to this orbit and the distance it was from the nucleus, it helped us to determine kind of energy levels and think of them kind of like steps on a ladder. Now, when you think about steps on a ladder, one thing that you should be able to recognize is you can't stand in between steps, right? You can either be on one step or on another step, but you can't be in between. You can have one leg on one step and one leg on another, but you're not going to be floating or levitating in between individual steps. And so the same thing is true with electrons. They're not going to hang out in between energy levels. They have to be on, again, kind of using the ladder analogy, on one of the rungs of the ladder. And so the number of energy, you number the energy levels, n equals 1, 2, 3, 4, so on and so forth, right? N equals 1 is going to be closest to the nucleus, and as we get farther and farther away, to those higher and higher numbers, that means that the energy level is farther and farther away from the nucleus. Now, using the ladder analogy, it's not a perfect example, because when we start talking about energy levels, they're different from the steps on a ladder, because most ladders, the steps are evenly spaced, right? Like if you're using a ladder, nice normal ladder, that's what you would expect, right? But when we start to look at these energy levels, what we start to see is that the rungs start off farther and farther apart, but then they get closer and closer together. And so I kind of like this representation. So you've got your nucleus, which is on the ground floor. N equals 1. This is the first rung in our ladder. That's going to be the lowest energy an electron can have. Then you've got N equals 2, N equals 3, N equals 4, N equals 5, N equals 6, N equals 7. And as we're getting farther and farther away, notice that the distance between each of the rungs on the ladder are getting closer and closer together. So there's less of a difference between those energies as we're getting farther away from the nucleus. And so that might not be a representation that you've seen before, maybe you have, but I think it's a good way to kind of visualize what's going on with those energy levels, right? So obviously the biggest differences are going to be between the energy levels that are closest to the nucleus moving to the farther away, or going from farther away to very close to the nucleus. And of course, as we move up the ladder, we're increasing the energy of the electrons, which leads us into our final model of the atom. Now, when we talk about the quantum mechanical model, what we know is that electrons do not follow in specific paths around the nucleus. It's not that simple. Based on like the Heisenberg uncertainty principle of being able to know the speed and the location of an electron, we can't know both at the same time. So we're limited in what we can know. So instead of following specific paths, what we believe or what we understand is that they pop in and out of existence so fast that it's kind of hard for us to keep track of. So really what we're determining is it's a probability. We can estimate mathematically that there's a probability that an electron is going to exist in a specific location, like a certain percentage, right? Like there's a 90% probability the electron is in this spot. And you can think of it like camera flashes going off. When a superstar walks in, or like at the red carpet, you got all these camera flashes, right? As they're popping off, that's kind of like the existence of the electron. It gets picked up in that manner. Now, quantum mechanics, which is an entirely separate field of physics, is used to help explain this particular behavior of the atom. And again, quantum mechanics is based on probabilities or chances that something is going to be true. Now, obviously within that, there's going to be some limitations to what we can know, because we're basing it off of probabilities. Now, the probabilities mathematically derived, so we're pretty confident in what those probabilities are, but it's based on those probabilities that something will be true. So something important to consider as we're moving forward. Now, the quantum mechanical model uses a cloud model to describe where the electron is going to be likely to be found. So it's not going to tell you exactly where it is, but it's going to give you a probability of locations where the electron could be found. And what we find is that these clouds take on particular shapes based on where an electron with a specific energy is most likely to be found. And if you're thinking back to what you know from AP chemistry, that's when you start talking about your s, p, d, and f orbitals and the specific shapes that those orbitals have. Right, so there's our model of the atom. We've got that dotted line representing kind of the electron cloud. You've got the positive nucleus, you got the red electron. And so what we can say, based on the quantum mechanical model, is that there's going to be a 90% chance that the electron is somewhere in here, in this region of space that's around the nucleus, right? That's been encapsulated within that dotted line. All right. Now, the last thing we need to talk about are orbitals, right? The quantum mechanics keeps the idea of energy levels, but they focus it in on using the periodic table as our reference, right? And so orbitals, also referred to as sublevels, atomic orbitals, they're referred to as s, p, d, and f. And then the shapes of those orbitals depend on what energy level that you're in. So remember, certain energy levels only have certain sublevels. So not all sublevels have, or not all energy levels have d and f orbitals, or even p orbitals, right? And we'll talk about this more as we move forward. All right, so that leads us to the end of our video. Thank you guys for joining me. Hope this has been insightful, and I'll talk to you guys again soon. Take care.